Hello guys, welcome back to my channel. Please remember to like and subscribe. Now today we'll be introducing you to sequence and series. And I wouldn't necessarily want to call it an introduction because most of the things we do in our daily lives follows a particular sequence. By sequence we mean it follows a particular pattern, a trend. There's some indication that we can actually make some prediction about it. So for instance, we may go to the supermarket every Saturday. That is a particular pattern. The Football World Cup is kept every 4 years. That is a pattern. The Olympics is kept every 2 years. That is a pattern. Even in terms of making predictions, we use sequences. We use it in problem solving. We use it in almost every single aspect of our daily lives. Look at it in chemical reaction, what happens when temperature changes over a period of time. Most of the things that we do have some sequence to it. Now, since we currently have a pandemic, I'm going to look at a hypothetical scenario. Now, let us say that we have a particular disease and we're going to talk about, let us say we discovered it and we have it, we call it day one. So let us say on day one, the number of persons infected is equal to 2. So that is what you find out on day one. On day 2, you find out that there are 4 persons infected. On day 3, we find out that there are 8 persons infected. On day 4, we have 16. Now, based on this pattern, on day 1 we have 2, day 2 we have 4, day 3 we have 8, day 4 we have 16. I can actually look at what is taking place here and make a prediction. So even before day 5 comes, I am saying that there's a very likely chance that on day 5 we're going to see 32 cases. How did I do that? That is because there's some pattern in here. If we examine the number of cases, we realize that there's a pattern here. And this looks like an exponential scenario. So we have 2, 4, 8, 16. All of these results occur as a result of powers of 2. So 2, which is the first scenario, is really 2 raised to the 1. The second one, which is 4, is 2 raised to the second power. Then you have 2 raised to the third power, 2 raised to the fourth power. So this goes on. So there's actually a direct connection between the day and the number of cases. So just looking at this pattern, on day 1 you have 2 to the 1, on day 2 you have 2 to the 2, on day 3 you have 2 to the 3. We can simply just create a function here. Let me call it f of t, where t is the time in days. This would just be equal to 2 raised to the t power. So if I want to make a prediction as to what will happen, probably on day 10, all I would have to do here is simply say f of 10, which would be equal to 2 raised to the 10 power. A very large number actually. So here I can make a prediction about what is to come. This will help me in decision making. Do I need to speed up the process in probably finding a vaccine for this virus or this disease? A lot of things can be done here. It will tell me what will happen down the line, a couple days from now, and how quickly I need to work to alleviate this pandemic. Here we have 4 examples of sequences. Now let us look at them one by one. Sequence A, we have 1, 4, 7, 10, and the ellipses here indicates that this sequence goes on. Now notice that I separate my terms in the sequence by a comma. Now what is unique about this sequence is that we have 1, 4, 7, 10. If you look carefully at the sequence, you would notice that we're actually going up by 3. So 1 plus 3 gives me 4, 4 plus 3 gives me 7, and 7 plus 3 gives me 10. There's a special name that we give to this sequence. We call it an arithmetic sequence. The second sequence, we have 3, 6, 12, 24. What is up in here? If we examine it closely, we notice that we're constantly multiplying by 2. So we multiply 3 by 2 to get 6, 6 by 2 to get 12, and 12 by 2 to get 24. Alright, this sequence is also infinite, so we call this is called a geometric sequence. Now, question C, or example C and D, are examples of finite sequences. And how do we know it's finite? We go up to 16 and we stop there. So there's no ellipses indicating that it does go any further. Now, these two sequences are neither arithmetic nor geometric. But that doesn't mean we can't define them. If we look at 149, we can still see a pattern. It might not be direct that I'm adding something directly or I'm multiplying by something, but this is a sequence of square numbers, 149, 16. If we look at D, a similar thing happens. We don't directly see a number being added or subtracted, but there we have the set of cubic numbers. So in order to master sequences, we must master the different types and sets of numbers that we can actually have. Very important and integral before we can start defining them in terms of using formulas and so on. We are first going to examine the arithmetic sequence. Now let's start doing this by using a layout. So let us say we have a sequence where the first term I'm going to call it T1, which means term 1, then term 2, term 3, and term 4. And the terms in a sequence are separated by a comma. Let us say this goes on and on. Now, this particular sequence is arithmetic. If when I subtract two successive terms, the result is the same. So if I go T2 minus T1, I should get the same result as when I go T3 minus T2. The same thing as when I go T4 minus T3. Now the result that I'm going to get here is what we're going to call a common difference, and I'm going to call it D. So that is my common difference. So when I subtract two successive terms, I should get that common difference, D. For example, let us say we had the sequence 3, 7, 11, 15. The first term here is 3, and the second term is 7. So when I go 7 minus 3, I should get the same result as when I go 11 minus 7, which should be equal to the same result as when I go 15 minus 11. Now let us check and see. Now 7 minus 3 is 4, so I'm going to end up with 4 equal 4 equal 4. So I know that this sequence is arithmetic because I'm constantly adding 4 to each term to get the term that comes after. So when I subtract these two successive terms, so the first term subtracted from the second term should give me the same result as when I subtract the second term from the third term. We could generalize this for the arithmetic sequence. So we could say that the common difference D for any arithmetic sequence is equal to the n term. I'm going to call it T subscript n minus the term that comes before that, which would be T subscript n minus 1. This is a general rule for any arithmetic sequence. To come up with a rule for this arithmetic sequence, I'm going to start by rewriting the sequence. So my first term is 3. My second term, which is 7, and notice here I'm constantly adding 4. My second term, which is 7, is really 3 plus 4. The next term, so each time we're constantly adding 4, so it means that I can write 11 as 3 plus 4 plus 4. The same approach would apply for 15. It would be 3 plus 4 plus 4 plus 4. And then for 19, it would be 3 plus 4 plus 4 plus 4 plus 4. Repeated addition is really multiplication. So instead of adding 4 plus 4 plus 4, I could say 4 times the amount of time I'm actually adding it. So here I could write this now as 3. Then I'm going to have 3 plus 1 times 4. Notice that is for the second term. Then for my third term, I'm going to have 3 plus 2 times 4. For my fourth term, I'm going to have 3 plus 3 times 4. So if you notice, the amount of 4s that I'm adding here is 1 less than the n term. What do I mean by that? When I go to the fifth term, it's going to be 3 plus 4 times 4. So I'm adding 4 4s, although it's a fifth term. So how can I actually define this sequence by the position of the terms? For the first term, if I wanted to fit in this particular sequence, I could actually say 3 plus 0 times 4. And then it picks up and goes on. So I know that the first term, which is 3, which is a constant, is always going to be involved in coming up with my formula. But for the first term, I don't want any 4's to be added. In other words, I need 0 4's to be added. So we could actually go ahead and say this is the same thing as saying 3 plus n minus 1 times 4. Why n minus 1? Because to get the first term, I'm going to input 1. To get the second term, I'm going to input 2. So we can actually define the sequence by the position of each term in the sequence. And let us see if this actually works. My first term is 3. So let me input 1 into the place of n. N represents the position of the term. When I put 1 in there, 1 minus 1 is 0. So I'm going to end up getting back 3. If I were to put 1 in there, if I were to put 2 in there, I would have 2 minus 1. Then 3 plus 1 times 4 gives me 7. So it does work. So this is how I define a sequence by the position of its terms. And of course, I could actually break this down. But before I break it down, based on this pattern, I could actually create a general pattern for the arithmetic sequence. So I could actually say any term, let me call that an, is going to be equal to the first term. As you can see, 3 was my first term. Let me call the first term a, plus n minus 1 times d, where d is my common difference. So let's define everything that we have in this formula here. A is going to represent the first term. N is the position of term. And of course, D is the common difference. Here's an example of a question. Find a formula for the n term of the following sequences. So my first sequence here is A, and the terms are 6, 11, 16, 21. Now by looking at the sequence, I realize that I'm going up by 5, because 11 minus 6 is 5, 16 minus 11 is 5, and 21 minus 16 is 5. So I established that this is actually an arithmetic sequence. Now we say for an arithmetic sequence, an is equal to a plus n minus 1 times d. Bear in mind that d is a common difference and a is the first term. So for this, the n term would be equal to a, which is 6, plus n minus 1 times the common difference, which is the number I'm actually going up by. And in this case, I'm going up by 5. Now, of course, we're not going to want to leave it like this, because we can actually tidy this up. So we could actually say that an is equal to 6 plus 5n minus 5. This now breaks down to 5n, and 6 plus negative 5 would give me 1. So 5n plus 1. So we tidy up whatever we get. Look at example 2. We have 63, 57, 51, and 45. And notice that this sequence is actually decreasing. But what am I decreasing by? If you notice 63, 57, so 57 minus 63, that's negative 6. 51 minus 57 is also negative 6. And 45 minus 51 is also a negative 6. So it is still arithmetic. But what is going to change here? Alright, once it's arithmetic, we go ahead and we say that an is equal to a plus n minus 1 times d, which is my common difference. In this case, we can see that the first term, which is a, is 63. But what is my common difference? No, it is not actually going to be 6, but it's going to be negative 6, because I'm constantly adding negative 6 each time to get the terms that comes after. So it is going to be times negative 6. Now, when I break this down, I'm going to have an equal 63. And of course, when you expand this bracket, you have minus 6n plus 6. So this boils down to give me an equal minus 6n plus 69. We're going to take a similar approach to looking at the geometric sequence. So let's say we have term 1, term 2, term 3, and term 4, and so on. Now, what makes a term geometric is that we are constantly multiplying by a common value. That value is what we call a common ratio. Now, By just looking at a sequence, how would I know that this is geometric? Because I can see that common value coming out. Meaning what? Means that I multiply term 1 by something to get term 2. I multiply term 2 by that same value to get term 3. I multiply term 3 by that same value to get term 4. Now what it means is that if I were to go term 2 over term 1, I should get the same value as if I go term 3 over term 2, which is equal to term 4 over term 3. This produces a constant value, and that value is called a common ratio, generally represented by a common R. For example, 3, 6, 12, 24, 48. What we're seeing here is that I'm constantly multiplying by 2 because 3 times 2 gives me 6, 6 times 2 gives me 12, and so on. But if I were asked to prove it, I would have to show that when I divide two consecutive terms, I'm getting that same value. So if I go 12 over 6, I should get the same value as if I go 6 over 3. And here I'm going to get 2 equal to, so it's actually geometric. Now, for this particular sequence, the question is, how do I find a formula that defines this sequence? We know that we are constantly multiplying by 2. So my first term is 3, but my second term is 3 times 2. My third term is 3 times 2 times 2. And my fourth term is 3 times 2 times 2 times 2. This can be condensed because we could actually write this as 3 times 2 to the 1, 3 times 2 square, 3 times 2 cube. So this is my first term, this is my second term, my third term, my fourth term. Now what is unique is that if you look at the second term, the power of the common ratio is equal to 1. If you look at the third term, the power of the common ratio is equal to 2. And if you look at the fourth term, the power of the common ratio is 3. So if the power of, if the term is n, the power of the common ratio is n minus 1, which of course is unique in this particular scenario. So if I wanted to involve the first term, I could really go 3 times 2 to the 0, and so on. So to come up with a formula for this, clearly I can see that the first term must be involved. So it's going to be 3, which is the first term, times the common ratio, which is 2, to a certain power. But that power is going to be 1 less than the position of the term. So if my position is n, the power of that variable is going to be n minus 1. So it's going to be 3 times 2 to the n minus 1. Now to generalize this, because whatever happens here, since this is geometric, a similar concept would apply with all geometric sequences. So to generalize, what we are saying here is that the n term, any term at all, is going to be equal to the first term, which is a, times the common ratio, which is r. So I can just say ar to the n minus 1. Now here, a would be my first term, and r would be my common ratio. Here's an example. Find the formula for the n term of the following sequence. Now, when I look at this, I can clearly rule out the arithmetic sequence because you can clearly see that there's a large difference between the numbers. It couldn't be the same, and it would have varied. Now, before I jump ahead and say that this is geometric, I need to check. Say if I were to divide 24 by 6, I get 4. I also need to check if when I divide 96 by 24, what happens? I still get 4. And if I were to even divide 384 by 96, I still get 4. So right away, I know that this is geometric. So we can start by laying down the formula that says that an equal ar to the n minus 1. Bear in mind that a is my first term, so I'm going to have 6 times r is my common ratio, and my common ratio here is 4. to the n minus 1. And this is the formula that we're going to be using, or this is the general formula for this particular sequence. Look at example B. We have 48, 24, 12, 6. By looking at this, we clearly see what is happening here. We start with 48, we go on to 24, and 24 is half of 48. We move from 24 to 12, and 12 is half of 24. So technically, we're actually halving the terms here. So right away, we can pick up that my common ratio is a half, and my first term is 48. So we can go right ahead and say that an equal ar to the n minus 1. My first term here, which is a, is 48. And of course, my common ratio here is a half, so I can go a half to the n minus 1. And this, of course, is the formula for finding the general term, or the n term, in this particular geometric sequence. Sequences don't always have to be arithmetic or geometric. Sometimes they fall in neither category. But there is always a clue as to how to figure them out. For example, what if I gave you this sequence? A, you have 1, 4, 9, 16, 25. By looking at this sequence right away, if you understand the different types of numbers, you could actually pick up that this is actually the sequence of square numbers. So to define this sequence, I'm just going to have an equal n squared. And of course, when I input 1 here, I should get the first term. So we input 1, 1 squared is 1. We input 2, 2 squared is 4. We input 3, 3 squared is 9, and so on. From this sequence, I could probably even derive a next sequence. Let me call this B. So what if I had 2, 5, 10, 17, 26? What is unique about the second sequence is that these numbers, so you realize it's neither arithmetic and it's not geometric, and you can always carry out a test to check. And these numbers are 1 away from a squared number if you compare it to question A. So I could say that the general term for the sequence an equal n squared plus 1. Let us see if that works. So we put 1 in there, 1 squared plus 1 is 2. We put 2 in there, 2 squared plus 1, that's 5.